This problem applies the Gibbs free energy equation in all the possible scenarios for a given magnitude of delta H and delta S. Let's analyze that. We know that the Gibbs equation, delta G equals delta H minus T delta S, will tell us when a reaction is spontaneous, provided that delta G is negative. That's important. So delta G has to be negative for the reaction to be spontaneous. And then look at the setup of the equation. Things that help a reaction be spontaneous would be a negative delta H and a positive delta S. That would lend itself towards a negative result when you're multiplying by a positive temperature in Kelvin. Importantly, temperatures in Kelvin, degrees Kelvin, are always positive numbers. In other words, the lowest you can go on the Kelvin scale is 0, and that's absolute 0. Let's make a little chart. If we list possible values, or possible signs rather, for delta H, delta S, and delta G, and then we consider whether or not the reaction is spontaneous. Let's just make a little chart. So first, let's say we've got a negative value for delta H. That's a helpful thing for making the reaction spontaneous. And then let's say we've got a positive value for delta S. If you've got a negative value for delta H and you're subtracting the quantity, a positive temperature in Kelvin, times a positive delta S, necessarily then the result would be negative for delta G, and we can say that that reaction would be spontaneous at any temperature. You could say always spontaneous. Let's consider a different scenario. What if you have a negative delta H? That's helpful in making spontaneity. But let's say that your delta S value is negative. In that case, you have a negative delta H, but a negative delta S multiplied by a positive temperature in Kelvin, but it's being subtracted. In that case, we don't know what the value of delta G is, but we can say that the lower the temperature, the better. Okay, another scenario. What if delta H is positive and delta S is negative? Well, if delta H is positive, that does not help spontaneity. And if delta S is negative and it's being multiplied by a positive temperature in Kelvin, that's going to give you a positive result, or a negative result after multiplying by a positive number, and you're subtracting it so that delta G will always be a positive number in that case. We can say then that that reaction would never be spontaneous regardless of the temperature. See the pattern we're setting up? Negative, positive, negative, negative, positive, negative. What if delta H and delta S are both positive? Well, in that case, we have a positive delta H. That does not help spontaneity. But a positive delta S multiplied by a positive temperature would help because it's being subtracted. As long as that quantity, T times delta S, can exceed the value of delta H, then we can make it spontaneous. The higher the temperature, the more likely it would be spontaneous in that case. So this scenario gives us spontaneity when temperatures are high. This chart will be very helpful when thinking about this problem. So consider the 4 scenarios. In question A, we have a negative delta H and a negative delta S. Negative, negative, we'll have to solve. This question A would be spontaneous when temperatures are low. So I'm going to say that's like question A. In question B, we have a positive delta H and a positive delta S. Positive, positive, that's another situation where we don't know. We're going to solve. This would be spontaneous when the temperatures are high. I'm going to put a B there because it's just like question B. How about situation in part C? We have a positive delta S and a negative positive delta H and a negative delta S. So it goes positive, negative. In that case, your reaction is never spontaneous. The value of delta G is always positive, and without even having to do any calculations, we can click never spontaneous. Okay, last one. In part D, we have a negative value for delta H and a positive value for delta S. Negative, positive. In that case, your value for delta G is necessarily going to be negative at any temperature. It's always spontaneous. And without having to calculate, you can just click the box that says always spontaneous. That leaves us with parts A and B. For parts A and B, we have to actually solve. If you're trying to find the temperature for the spontaneous, non-spontaneous tipping point, we can use the Gibbs free energy equation, and we're going to plug in 0 for delta G. That is the point at which it's in equilibrium between being spontaneous and not spontaneous. And then we're going to plug in the values they gave us. A negative 18 kilojoules for delta H. And from that we're going to subtract the temperature, which we'll solve for, minus delta S, or times delta S. Look closely at the units. The delta S units are customarily given in joules per moles times degrees Kelvin, or just joules per degree Kelvin. The units for delta H are customarily given in kilojoules. Because we're subtracting one from the other, we have to make sure that those units agree. So let's take the negative 60 joules and divide by 1,000 to make it negative 0.060 kilojoules per degree Kelvin. So this is a negative 0.06. When we solve, let's see, we get 18 equals, the negative signs cancel out, so t times 0.06. Solve for t and you get 300, and this would be degrees Kelvin. Let's look at our chart again. This reaction would be spontaneous when temperatures are low. So we would click the option that says spontaneous when temperatures are less than 300. 300 is the tipping point. All right, let's consider part B. We have the positive scenario. Again, it's the Gibbs free energy equation, and we're going to plug in 0 for delta G. And this time it's a positive 60 joules, which if you convert to kilojoules is 0.06. The temperature, again, is going to solve to 300 because that's the tipping point. And if we look at our chart, this reaction would be spontaneous when the temperatures are high. So temperatures above the tipping point. I would choose that for your answers.